All right. So, we did classical field theory so far, no. So, classical field theory has a definite evolution for the field, like a particle in classical physics takes a definite trajectory following the equation of motion. Similarly, fields also follow equation of motion and its definite trajectory, like we can think of a string which is oscillating and there is no ambiguity, right. I mean, the given time we can compute what should be the profile for that string, okay. Or same for electromagnetic field which is classical, it is definite given the initial condition and boundary condition we can find the evolution. But now we are getting into quantum mechanics, okay, where the field will not be definite, okay, field will have uncertainties, field will become operators. So, the complications start now and of course, the richness also start, okay. So, we are getting into quantum field theory from now on. So, let us just do the particle quantum mechanics right now first, okay, 3 slides just to review, and some of it is going to be directly ported into fields. So, reviews of quantum mechanics. So, general principles, okay, uncertainty relation, no, that is so position and momentum are not accurately measurable in quantum mechanics, okay. So, it is not, I mean, particle in fact lives in a abstract space, it is not in real space. So, particle position momentum become indeterminate, in fact they are operators and they follow commutation relation, okay. This is a commutation relations. A Schrodinger equation yields a wave function evolution. So, from the wave function you can compute position, momentum, energy and so on. This is a Schrodinger equation, okay, using which we find psi, and from psi we find expectation value of the physical quantities like position, energy and so on. Properties derived from the wave function, and so for bounded system we have energy eigenvalues, right. For Schrodinger equation, for hydrogen atom we have bound states, and for scattering states we have scattering of the wave function and so on, okay. So, normally, okay, it is easier to work with evolution of psi t, right, psi is evolving from here, right, from Schrodinger equation, or sometimes we make the operators evolve in time, okay. So, the Heisenberg picture, the Schrodinger picture, Heisenberg picture, and third is interaction picture, okay. I am not going to get too much into it, but we will use well field theory uses Heisenberg picture, okay, most of the time. So, we will come to that in 10 minutes. So, first quantization, this is called first quantization, we have position and momentum for classical particles, but now we quantize it and we basically go to wave function instead of x and p, and from wave function we compute various physical quantities which are expectation values, they are not determinate, okay. So, this is called first quantization for particles, okay. This is loose word, but you can just think that is the first quantization. Now, let us look at an example linear oscillator, which is going to come again in field theory. So, linear oscillator, right, half m, well, so we know the oscillator mx double dot is minus omega squared x, m omega squared x, okay. So, mass of the particle m, frequency of the oscillator is omega and it is linear, and this is classical equation. Now, in quantum mechanics, of course, we have to solve the Schrodinger equation, and x and momentum become operators. So, the Hamiltonian for quantum oscillator is this p squared half plus half x squared, and both p and x are operators. So, operators I am going to write as a hat, this did not come out well in PPT, okay. Now, by change of variable, all of I am sure you know this change of variable, this creation operator a, which is x plus I p by square root 2, a dagger, which is a dagger, I made so this I think is a dagger, okay. So, a dagger is x plus I p, and a, which is a is a destruction operator, and its meaning becomes clear when field theory, okay. So, right now it is not clear, but we will come to that this creation. I am not 100% sure about the sign, but let us go ahead with that. So, Hamiltonian is A dagger A plus half. So, this you can just substitute it here, use the commutation relation and you will get it. Okay. Half is coming from the commutation relation and it has a very important consequence. Okay. The ground state energy is non-zero for oscillator because of that half. Okay. So, A dagger A, this is our number operator and there is a number state. Okay. This derivation I will not do it, it is done in standard quantum mechanics course. So, no point repeating it. So, n is a eigenstate for A dagger A, which is an operator and it gives you number n. Okay. N is the level, that is what it is supposed to be. So, n is a positive integer, positive definite integer. Okay. So, n can be 0, 1, 2, 3, 4 like that, n cannot be negative, it can be proven. In energy is n plus half. Okay. Now, I am normally going to put h bar as 1 and omega, in fact, this is a total energy, but h bar we set it to 1. So, energy is n plus half h bar omega and these operators a n is square root. So, A is a destruction operator. So, it will basically bring down the state from n to n minus 1. Okay. And the prefactor square root n, we need to remember this, square root n is a prefactor when it comes down to state n to state n minus 1. This is oscillator, it has all these eigenstates, energy eigenstates. So, we start with 0, 1, 2 like this, right. So, if I apply this A operator, then I come down from, let us say on 2, then it will go to 1, comes down by 1 state. Okay. Hamiltonian, of course, if I operate h on 2, then it will remain on 2 and will give the eigenvalue n plus half. A dagger will take it up. A dagger is a creation operator which takes it to n plus 1. So, A dagger acting on state 2 will give you 3 is the prefactor, and what is the prefactor? Square root 3. Okay. So, higher of the 2. So, you have left state and the right state, the prefactor is always square root higher number. So, here it is square root n plus 1, because n plus 1 is bigger than n, well, is the maximum of n plus 1 and n. Here it is n and n minus 1, so it is square root n. Okay, that is a easy way to remember. Okay, the vacuum state or the ground state, for here right now we should think of the ground state for single particle. A acting on 0 gives you 0, it cannot go below 0, below the ground state, no. So, this is in fact vacuum is for future, this is ground state. Okay. Ground state does not have 0 energy. Classical oscillator, if it is a equilibrium state or ground state, then it has 0 energy, it is particle is sitting at a position with a spring which is unstretched. So, that is the lowest state and which has 0 energy, but oscillator, because the uncertain relation has non-zero energy. Okay. And its energy is, how much is energy? Half h bar omega. Okay. And we will see that in field theory this plays a big role, and this is purely quantum. So, this cannot be derived classically. Okay. So, this is a brief review of quantum mechanics which everybody knows. I am sure there is no question on this.